Linear regression in R. In this video, I'll talk about how to use the linear regression model in R to solve real problems. Linear regression is a predictive modeling technique. It is used to find a mathematical equation for a continuous response variable y, which is called as dependent variable as well. As a function of one or more x variables, and the x variables are called as independent variables. So that you can use this regression model to predict the y when only the x is known. The expressions look like that. Y equals to beta 1 plus beta 2 times x plus epsilon. Beta 1 is the intercept and beta 2 is the slope. They are called regression coefficients, and epsilon is the error term, the part of y the regression model is unable to explain. I have an xy coordinate system. And the linear of the expression looks like that. The beta 1 is the intersection between this line and the y-axis. Then the slope of this line is what we call as beta 2. And the original data may look like that. When we use this expression to predict the y value, for example, the data point of this blue one, and x equals to 0, x0, and then when we predict the value for 8, we need to go onto the line and find the y0 over here. So we can see there's a distance between the estimated value and the real y value. The distance is what we call as epsilon, the error term. Example problem. The cars dataset is a built-in dataset in R. It consists of 50 observations and 2 variables. 2 variables are distance and speed. We can use the head of cars to get the first several lines or several observations for the cars and use the summary to get a summary for each column separately. The goal here is to establish a mathematical equation for dist as a function of speed. So the dist is the dependent variable and the speed is the independent variable. Use it to predict the dist when only the speed of the car is known. The graphical analysis. This is what we call as EDA, and the EDA example is the book price assignment. Use the EDA or mainly the graphical analysis gonna help us to understand the variables graphically and have a better understanding of those data. So the box plot, it used for checking the outliers. An outlier is any data point that lies outside of the 1.5 times the interquartile range. And this is the R code for running the box plot. And over here we can see there's one outlier for the distance. However, it's not very further away from this range, so I decided to keep it. You can make your own decision. If you want to remove it, please make a full discussion on why you think we should remove it. And then go back to our scatter plot. Scatter plot gonna help us to visualize the linear relationship between the predictor and the response. Again, this is the R code, and this is the scatter plot for the speed and the distance. Inside of the scatter plot image, it suggests a linear and a positive relationship between the distance and the speed. One of the outlier assumption of linear regression is the relationship between the response and the predictor variable is linear and additive. Ideally, we should find a straight line that goes through all of those data points. Over here, there's a line. It's not perfect. However, we still can cut it as linear line. And then they have the linear regression between the speed and distance. Again, we have the positive relationship between those two variables, that as the horizontal goes up, the vertical goes up as well. That is what we call it as positive relationship. And just like what I mentioned, it means the assumption, one of the assumptions of linear regression, linearity. There are several other assumptions of linear regression, and we just look at the linearity. Then the first one is independent of observations. Actually, it's very hard to check the independence for the observations over here. So just to make the assumption that all the observations we used for our assignment are independent. And then we need to check the normality. How to check the normality? Previously, we learned we can use the histogram to check the normality, and here we introduce into a new function, the density plot. We're gonna check the distribution as well. This is the R code, and this is the output. We can see the speed follow the normal distribution, and the distance is a little bit right skewed. However, it's not extreme right skewed, so I decided to use the original distance. If it is skewed too much, we might need to take a log or other transformation of the original variable to make it distribute normal. Okay. And then we need to build the linear regression model. You have seen the linear relationship in the scatter plot, and we have also checked the normality of the distribution. Then we can use the function to build up a linear model. That is LM. The LM function takes in two main arguments. The first is formula, and the second is data. The model, which I named it as linear mode, you can have whatever name you like, and use the LM to build up the linear mode relationship. And again, the dist is the dependent variable, and the speed is independent variable. The data is cars. Then you can print the linear mode outside to get the coefficients. This is the intercept, the beta 1, and this is the slope, the beta 2. So over here, we can see we build up the linear regression model. That is our formula. So after we build up the linear regression model, we need to do the diagnostics to ensure that it is statistically significant. Use the summary of the linear mode. We can check the p-value as well as the r-square. The p-value for here, I want them to be less than level of 0.05. If so, we can see that it is statistically significant. and then the R square. R square tells us the proportion of the variation in the dependent variable that has been explained by this model. And remember, when we talk about the assumption, there were actually 4 assumptions that we need to check. We have already checked the independence and the normality by the density plot or histogram. The linearity has already been done by the scatter plot. We haven't done the homozygosity yet. How should we do that? So we want to do the more diagnostics to check the assumption. Then this is my R code, and this is the output. There were 4 different images got printed out, and for now we just look at the first one and the third one. So ideally, the residuals plot will show no fitted pattern. That is, the red line should be just about horizontal at 0. That presents a pattern may indicate a problem with some aspects of linear model. So we can see that the red line is almost horizontal and just through the 0 line. And then the third one. This plot shows if residuals are spread equally along the ranges of the predictor. It is good if you see a horizontal line with equally spread points. So in our example, it is almost look like that. Then that is the way to check actually the 4th assumption, that is homozygosity. And if you want to just use the 3rd plot from this diagnostics, you can write down like the plot, and inside of the parentheses is the model name, comma 3. In that way, you're gonna just end up with the 3rd image. Then because we check the diagnostics, then we can see the predicting linear mode looks like that. Then the predicting linear mode is just being set it up, and the preferred practice is to split your data set into 80 versus 20 sample, and the 80 works as training, the 20 works as test. Then make assumption. Making assumption is super important. Inside of the conclusion, make a conclusion. Inside of the conclusion, you have to cover, do you believe you can use the linear regression? The 4 assumptions, maybe at the beginning, you just need 3 assumptions. And what is your model and linear relationship you find? How does this model behave, like p-value, R squared, or the performance? If you split your data set into like 80 versus 20, then you can use this 20 to check the performance. At the end, how do you want to use your final model to do the predictions? For example, we have this final model. We can see when the speed equals to 2, I can predict the distance value based on this formula. And when the speed equals to like 50, we can predict the distance value as well. So if you split your data set into 80 versus 20, you can use this 20 value to check the performance. Like when you predict the value, you can check with the real distance value to see how far away between those 2 values to see whether your data set, your performance is good or not. That's it.